We'll start with an alternate solution for two sets, which was shared by Pratik yesterday, and we'll just take a close look at that solution. So this solution, unlike the previous solutions, this solution consumes linear space. This consumes extra memory, linear space. But regardless, this is a very interesting solution, I think, because we can go through some of the reasoning about the solution and see why the solution works with some rigor. So that's my intention here, to go through the solution. Let's see how the solution looked. So Pratik shared a Rust program yesterday. So this is just a description of the solution, and I have some code as well in C++. Let us see the description. The solution works like this. For each integer k from k in n to 1, so we'll go in descending order, we'll go with k equals n minus 1, and so on, all the way to 1. If the sum of the integers in the first set, so we're maintaining two sets, it could be two vectors, for example, in C++, we're maintaining two lists or two sets. If the sum of the integers in the first set is less than or equal to the sum of the integers in the second set, add k to the first set. Otherwise, add k to the second set. In simple words, what we're doing, we are maintaining two sets of numbers, and we are picking every new integer, and we're checking which set has the smaller sum, and we're going ahead and putting our number to that sum. So this is a continuation of yesterday's problem. If anyone here is not familiar with the problem statement, just let me know. I'll open the problem page once again for your convenience. If everyone is fine, I'll just move ahead for now. So that is the basic idea. The basic idea is check which set has a smaller sum, in fact less than equal to is the comparison we'll do, and put our number there. And here are two illustrations to see how the solution works. So the first illustration, okay, I'll keep it until here, is for n being a multiple of 4, and the second illustration is for n being a multiple of 4 plus 3, because those are the two types of numbers that give us solutions. We know that if n is a multiple of 4 plus 1, or if n is a multiple of 4 plus 2, we don't have a solution. We discussed that in detail yesterday. So for now, we'll just focus on these two types of n and see if it is guaranteed to arrive at a solution following this approach. So when n is a multiple of 4, and we follow this algorithm that I have written down here, this is how the set building will progress. So this top row is showing what happens to what numbers we put in set 1. This bottom row, or the second row, is showing what numbers we put in set 2. So we start with empty sets. Both sets are empty. So as per this rule, we'll go ahead and put 12 in the first set. So that is the less than equal to comparison we are doing. And then we check 11 now. We need to put 11 somewhere. And obviously the second set is now empty, so it has a smaller sum. We go ahead and put 11 in the second set. Now we have to put 10 somewhere, and we have only put these two numbers in both these sets. So again, set 2 has a smaller sum. The sum of the numbers in set 2 is 11. The sum of the numbers in set 1 is 12. So this has a smaller sum. So we go ahead and put 10 in the second set. And we keep going like this. And then 9 will go in this set, because now this set has a smaller sum. It only has 12, but this has 21. And we keep going like this, and this is how all the numbers get put into these sets. And you can see it follows a snake-like pattern, the pattern in which we put the numbers. That is the pattern it is following. And in the end, we have a solution where we have equal sum on both sets. Now, just by looking at this pattern itself, we can start forming some intuition. The question that we need to think about is, will we always have a valid solution following this approach? And we can start building some intuition. So what we are seeing here is that if we just take this as a group, like these two numbers and these two numbers. So we split this arrangement into 3 groups, each group containing 4 numbers. And we see that the sum of the integers in each group, or the integers in each group, will be satisfying the equality of sum condition. So for example, say we have put 12, 11, 10 and 9, and that is all we have done so far. The equality of sums in both sets is now satisfied, because 12 plus 9 is 21, 11 plus 10 is 21. And that is because What we are doing here, we are taking the largest, so out of these 4 numbers, we are picking the largest one and the smallest one, 12 and 9 in the first set, and then the middle 2 numbers in the second set. So sum remains equal. I think we'll also see it algebraically. I think I have a board or I have some notes for that to see it more algebraically. And the same condition holds true for each group of 4 numbers. So that is how this pair and this pair have equal sum, and again this pair and this pair have equal sum, and this pair and this pair have equal sum. So again, I'm talking in terms of intuition, a visual way of validating things. We need to make this more rigorous and really show that this pattern will always hold good. So that is for n being a multiple of 4. What about n being a multiple of 4 plus 3? Let's take a look at that. So n being a multiple of 4 plus 3, this is how the solution will go. Again, the method is same, except that in the end we are left over with something like this, where we have an extra number 1 in the second set. Once again, each group of 4 numbers that we are putting will follow the equal sum condition. So 11 plus 8 is 19, 10 plus 9 is 19, and it holds for all of this, including the last group, which is only 3 elements, because here we have 3, here we have 2 plus 1. Now, since this is a multiple of 4 plus 3, this is how we'll always end up with. We'll have a group of 4, another group of 4, and then maybe more groups of 4, but the last group will have 3 because we have a number n of the form 4k plus 3. That is a multiple of 4 plus 3. So intuitively, it looks like this should always work. And let's do a proof for it. It's more like an outline of proof, because I don't want to make it too rigorous, because it takes time to establish the notation and a proper language for making a proof too rigorous. So what I'm giving is an outline of a proof to show that this pattern will always hold good. Let us see this for n being a multiple of 4. So when n is a multiple of 4, we first show that we can approach it like a proof by induction. That is one way we can do it, or we can just build the solution recursively. So we can, or not really recursively, we're not actually coding a recursion, but show the argument recursively, that we start from a big number and then we show that the solution can be something about that big number plus solving the problem for a smaller number. So it can be seen either ways, top to bottom or bottom to top. I'm showing the top to bottom approach here, but I'm showing one base condition right away in the beginning. So this is the base condition. We first show that we can obtain a valid solution for n by following the solution algorithm. I missed something here. What I meant to say was that we can show a valid solution for n equals 4. That's what I meant to say here. I did not type it properly, but this illustration clarifies it. So if you're given n equals 4, we can obviously make a solution like this. Very easy. 4 plus 1 is 5, 3 plus 2 is 5. Now for n greater than equal to 8, we add the integers n minus 1, n minus 2, n minus 3 into the 2 sets like this. And this is this first group arrangement here, 12, 9, 11, 10. So what we're showing here is that this pattern will hold true for any n greater than equal to 8. I've chosen 8 because the next possible number for n is 8. It is a multiple of 4. So we can see that n plus n minus 3 is 2n minus 3. N minus 1 plus n minus 2 is 2n minus 3. What we have shown that we can, at least the first group, we can arrange it while satisfying the equal sum requirement. And then we solve the problem for n minus 4. And n minus 4 is another multiple of 4. So again, we can rearrange like this and so on until we reach n equals 4, in which case, obviously, we have a solution. So that is how we have shown with certainty that given any multiple of 4, we can create a solution like this, as specified in this illustration. And the argument for n being a multiple of 4 plus 3 is also very similar. We will first show that we can obtain a valid solution for n equals 3. That is something I missed there. So n equals 3, and the solution obviously looks like this: 3 and 2, 1. They both have equal sums. The sum in the first set is 3. The sum in the second set is also 3. Now for n greater than equal to 7, because we are dealing with numbers of the form 4k plus 3, the next such number is 7. So for any n, greater than equal to 7, we add the integers n, n-1, n-2, n-3 into the two sets in this fashion, which is no different than what we did earlier. And then we solve the problem for n-4. So n is a multiple of 4 plus 3. So n-4 will also be a multiple of 4 plus 3. That is by modular arithmetic. So again, we can use the same strategy to solve it for n-4, and we can put some more numbers on the right hand side, and we keep doing this until we reach n equals 3, for which we obviously have a solution like this. So that completes the description of this alternate solution. Of course, it consumes extra memory because we'll be keeping these numbers in two vectors or two lists temporarily. So this is what the solution would look like. I don't think there's anything interesting to explain in the solution. It is just coding this thing. But yeah, so here is my first set, here is my second set, v1 and v2, and I'm doing this comparison and just pushing the numbers either into v1 or v2. At the same time, I'm keeping the running sum for both the sets, sum1 and sum2, that is being used in this comparison. In the end, we're just printing out the results from both the sets. Yes, so this is where we'll stop for this solution, two sets. So we have covered, I think, 3 approaches so far of solving this two sets problem. If there are any comments about this, any questions about this, please feel free to post on chat or just unmute yourself and talk about it. Okay, if no comments, in that case, we'll move ahead to the next problem. For that, I need to visit the CSES website. Let me do that. And here, I'll just keep a scratch buffer open. Okay, yeah, I've got something written in the scratch buffer. We'll take a look at it if we get time today. So let me open the website now, cses.fy. The problems, and the next problem that we have today is bit strings, I think. No, this is something we saw yesterday. We have trailing zeros. Yeah, this is an interesting problem. This used to be actually little mathematics puzzles in my high school days. So the problem is based on that puzzle, and it's a very simple problem. The problem looks like this. So given a number n, we need to tell how many trailing zeros are there in n factorial. So it would be good if you don't have to compute n factorial, because n factorial can be very big. You can already see this is beyond, I think, the range of long, or maybe this fits. Yeah, but it is not hard to imagine that 21 factorial or 22 factorial will be definitely beyond the range of long. I think I have a board for that. Let me just see. But for a much later problem, just to see which factorial fits within the range of long. Do I have a board on factorial? Yeah, I have it here. Okay, so 20 factorial does fit within the range of long. So this is the maximum size for a 64-bit signed integer. 20 factorial does fit in it, but 21 factorial does not. Okay, so that's something interesting to know. But our n can be very large, so obviously we cannot really compute the factorial to determine the result. What we need to do is find some clever way to find how many trailing zeros will be there in the factorial. So that is the question here. The only input line has an integer n. Print the number of trailing zeros in n factorial. For example, if you're given 20, we should print 4. There are 4 zeros. So let's begin. Before I begin, if anyone wants to share any approach about this quickly on chat, please feel free to do so. But now I'll just start building the theory behind the solution. So I've taken an example, small example, 10 factorial, because it's easy to see and work out the underlying concepts with a small example like this. So the result is this. This is a known result, 3628800. This is what we need to report in our output, that it ends with 2 zeros. So how do we do that? We take a look at its factors. So how is 10 factorial made? It is made of these factors, 1 times 2 times 3 times 4 times and so on up to 10. And then we do a prime factorization of each of these numbers. So 4 becomes 2 squared, 6 becomes 2 times 3, 9 becomes 2 cubed, 8 becomes 2 cubed, 9 becomes 3 squared, 10 becomes 2 times 5. We have the prime factorization. And how do we get tens, or how do we get multiples of tens, which every multiple of 10 will contribute? Not really multiple of 10, is the power of 10 that contributes these zeros. So if this number has 10 as a factor, we get a 0. If this whole product has 100 as a factor, we get 2 zeros, and so on. So we get each power of 10 by taking a 2 from here and taking a 5 from here. That's how we get. So 2 times 5 is 10. If we take another 2, another 5, we get 10 times 10. 10 times 10 equals 100. And that is what happens in this specific case. We can take one 2 from here, one 5 from here, another 2 from here, another 5 from there. So we get 10 times 10 equals 100, and that is why we end up with 2 zeros. So the problem now is to find how many 5s can we find in this whole product. So in a more formal fashion, what we're asking is, what is the largest power of 5 that divides 10 factorial? So that is the question we are asking. So the problem, what looked like a big problem, is now reduced to a very specific mathematical question. What is the largest power of 5 that divides n factorial? And why are we only focused on 5? Why are we not focused on 2? One thing, quite intuitively or visually, we can already see that the power of 2 will be greater than the power of 5. That's pretty easy to see, because there are more multiples of 2's than there are multiples of 5 in a finite number of factors like this. So that's the reason. If we just focus on the power of 5, that will tell us the number of zeros at the end of 10 factorial. So let us try to find that. I'll choose 2 for now. So instead of asking how many powers of 5 are there, I'm just making it a very abstract mathematical question. So let us not focus on 5 or any specific prime. Let us just ask a simple question. What is the greatest power of a prime that divides this 10 factorial? I'm choosing 2 on purpose, even though I said that 5 is what gives us the solution, just to demonstrate the underlying mathematical concepts. So the question, I'll just shift gears now and ask a slightly unrelated question. What is the largest power of 2 that divides 10 factorial? And let us learn to solve that. And then we'll use the same technique for 5. So here it is worked out, and I chose 2 because the computation takes a little more time to do, and that helps us see the underlying patterns a little bit better. That's why I chose a smaller prime here. So power of 2 that divides 10 factorial. So let us look at all the powers of 2 that are present in this, all the multiples of 2 that are present in this list of factors. So they are 2, 4, 6, 8, 10. Each one of these numbers, even numbers, 2, 4, 6, 8, 10, will contribute a factor of 2 each. Okay, so we are getting 5 number of 2's from that. So 2 to the power 5 is a factor that we're getting from 2, 4, 6, 8, and 10. Then let us look at all the squares of 2. So for example, 4, not really squares of 2, all the multiples of 4. Okay, I said that wrong. We looked at all the multiples of 2, then we look at all the multiples of 4, and they will contribute one more 2 as a factor in addition to what we have seen so far. So 4, because this is 2 square, this is contributing yet another 2, and this 8 is contributing yet another 2. So we got 2 more 2's from 4 and 8. Now we'll look at multiples of cubes of 2, that is 2 cubed. So 8 will contribute yet another factor of 2. So that is the pattern we have to notice and try to capture in a formula. And if we had more terms, we would have got more, like the next 16, the 8 and then 16 would have given us yet another factor. What we are seeing, that we are the first bunch of factors, or the first bunch of 2's, we are getting from 5 numbers in this list, which is 10 divided by 2, because there are 5 multiples of 2. Okay, so that is captured in this formula here. Let me see if I can increase the font size, or maybe I can do something like this: style equals font size 8px. Oh, it's too big. Yeah, something like this. Just want to show these superscripts properly. Okay, so this is representing how many times we have collected these 2's. So we are getting 10 by 2 floor, and that floor will become clear in a while, because that is representing the number of multiples of 2's we have here. We have 5 of them. Then the multiples of 4. How many multiples of 4 do we have? We have 2 of them, and that comes from 10 divided by 4 floor of that, and that is 4 and 8. So they contribute 2 more 2's, and then how many multiples of 8 we have? And they, each one of them contribute 1 more 2 each. So that is how we are getting 2 to the power 8. So we are seeing that in this 10 factorial, we have 2 to the power 8 present. 2 to the power 8 divides this 10 factorial. That is how we solve this problem, considering 2 as the prime for which we want to find the greatest power that divides 10 factorial. In this case, 2 to the power 8 is the greatest power of 2 that divides 10 factorial. And this thing in number theory is also called the Legendre's formula. In fact, in this club of bit computation club, the way we call it, we used to have analytic number theory sessions before, and we did go through this Legendre's formula in those sessions. So here it is summarized once more. So if you have not come across this formula ever before, it's nothing to worry. I'm just putting the exact same formula here once again on this board. This is how it looks, and let me just break it down. So n factorial is a product of powers of prime, and that is just the prime factorization, nothing new there. Now what would be each of these powers? That is expressed like this, and this is just showing what we learned in the previous board in terms of a formula. So this is showing that this you can forget about for now. This you can work out on your own, like this would be the upper limit, but that is not important. What we want to see here is that we will take that number n, like in our case it was 10 factorial, and then we will divide 10 by the prime, and then we will collect the first set of factors, the count of the first set of factors. Then we'll divide this 10 by square of the prime, and then we'll divide this 10 by the cube of the prime, and so on. And that is how we count all the powers of that prime that divides 10 factorial. So here it is once again worked out for 2. So we get 8 number of times in that list, and that is how we know that 2 to the power 8 is going to divide 10 factorial. If you had started with 5, it is not so interesting because there are very few terms, but at least this shows the correct answer. That is, we have 5 square that divides 10 factorial. There is no larger power of 5 that divides 10 factorial. So this is the formula that we need to work with. We need to keep dividing the number that we have got by 5, because 5 is the number is the prime factor that we are interested in, and then we will raise the power of 5. We'll make it 5 square and then 5qm, and just keep collecting the answers. So let me see if I have a code for this. This problem is called trailing zeros. Yes, so this is how the code looks. So what is this alpha? Okay, I'm just keeping the code consistent with this notation here. Alpha, so alpha is counting the largest power of 5 that divides n factorial, and power equal 5. This is the powers of 5. I wrote this code some time back. I don't know what is going on. Let me just figure it out as I read through this code. So we want to calculate alpha like this: n by 5 factorial, n by 25 factorial, n by 125 factorial, and so on, and add them all up. In this case, I'm using the square bracket as the floor symbol in this case, and as long as this power is less than equal to n, we are talking about, okay, yeah, I got it now. So what we will do, right now it is 5, but I'll make it 5 square in the next iteration, and then I'll make it 5 cube, then I'll make it 5 to the power 4. So as long as that power is less than equal to n, it is not exceeding n, we have some work to do, because once it becomes, if 5 to the power something that is greater than the n, then it will obviously not divide n. Anything that divides n has to be less than or equal to n. That is why this condition. While this power is less than equal to n, I am doing a float division here, n n divided by power. It's actually a truncated division, but since we're dealing with positive integers, that is the same thing as float division. And I'm collecting it in this alpha. This is my accumulator for that sum. So all these divisions, the floor of those divisions is being collected here, and then I'm increasing the power of 5 by multiplying it with 5. So now this power has become 5 square, and we'll do the same thing, that this power will become 5 cube, and so on until we reach until we start exceeding, and at which point we know that we'll not get any more factors. So yeah, so this is the solution for this problem. So once again, I'll stop here to check if there are any comments to be shared by anyone, or if you have solved it with a different approach, please feel free to share them. If you have a different way of coding this, please feel free to share the link to your solutions as well. Okay, no comments about this question, in which case we will move on to the next question, which is quite interesting. I'm not sure whether I can fit this entire solution in in the remaining 10 minutes. Maybe it may require 5 extra minutes. Let us see how it goes. So here's the next question: coin piles. So it's a big problem statement. Let us go through it. You have 2 coin piles containing A and B coins. On each move, you can either remove 1 coin from the left pile and 2 coins from the right pile, or 2 coins from the left pile and 1 coin from the right pile. I'll just summarize this. So we have 2 coin piles with some number of coins, and in each move we can pick 1 coin from one pile and 2 coins from another pile and remove them. Your task is to efficiently find out if you can empty both the piles. Okay, so that is the question. So can we empty both the piles successfully in the end by finding out some moves? Okay, so and then we have some input, and then the input looks like this, as an integer t, the number of tests. Okay, so that is not interesting. And then each line has the actual input for our problem. So 2 integers a and b, and they contain the number of coins in each pile. So this is saying the first pile has 2 coins, the second pile has 1 coin. And can we, for each test, print yes if you can empty the piles and no otherwise? Okay, so we can see that for 2 and 1 it is very easy. We'll just remove 2 from first pile, 1 from second pile, and it's done. We are done. So the answer is yes. For 2 and 2, there is no solution. We remove 2 from one pile, we remove 1 from the other pile, we are left with 1 coin, and there are no more moves we can do to remove that 1 coin, because we have to remove 2 from one and 1 from another. So no solution for this. For 3 and 3, again we have a solution. We'll remove 2 from this, we'll remove 1 from this, and then we are left with 1 here and 2 here. So we can just remove 2 from here and we can remove 1 from here. So we have a solution, yes. So let's start looking at this once again mathematically and see when we get a solution, when we do not. So the necessary conditions are quite easy to arrive at by intuitively looking at the problem, and then I'll make it more rigorous as well. So here I'm just trying to build some intuition for the problem, and the next board will make it more rigorous. So one thing that is very easy to realize is that a plus b has to be a multiple of 3. So for example, this is a multiple of 3. 3 plus 3 is 6, and we're getting a solution. 2 plus 2 is 4, and we cannot have a solution for a situation like this. And what is the reason for that? The reason is, in every move we are removing 3 coins, 1 from one pile, 2 from the other pile. In every move we are removing 3 coins. So if we want to make both the piles empty, the total number of coins has to be a multiple of 3. So that becomes a very easy condition. It's a necessary condition. It has to be true, otherwise we will not find a solution. That's the meaning of necessary condition. That one was easy. The second one, also we can try out with some examples. This says that one thing I did not clarify, okay, I have it. In all this analysis, I'm assuming a is less than or equal to b, just to make it simpler to reason about. And I've noted here, without loss of generality, say the problem has b greater than or equal to a, we can just flip around the numbers and just assume for the moment that a is less than or equal to b and do our analysis with that. So one of the two piles has a number that is less than or equal to the other number. We'll just call that number a. That's how we're starting the solution. Now if a is less than b by 2, again we'll not have a solution. And just take an example. Okay, so let us assume a is 5, b is 10. Okay, this is an example for which we will have a solution. A is 5, b is 10. We can remove one number from a and two numbers from b in each move, and we can make both the piles empty. So a has 5, b is 10, exactly double. But let us say a has 5 and b has, let us say, 18. Is that a correct thing? A has 5 and b has 10. No, sorry. A has 5 and b has 13. Let's take that as an example. Okay, it's still a multiple of 3. The sum is a multiple of 3. But we cannot make both the piles empty. And that is because a has 5, b has 13. Even if every move consists of removing just 1 from a and 2 from b, when we have reduced that a from 5 to 0, b will be reduced by 10. So b will be reduced from 13 to 3, and we are left with 3 coins that we cannot remove anymore because there is nothing left on the other pile to play any moves. So that is the reason a has to be less than b by 2. So b can at most be double of a, but b cannot be more than double of a. B cannot exceed the double of a. That's what I mean. And that is explained a little bit more formally here. If a is less than b by 2, the pile cannot, both piles cannot become empty. That's how I should write it. Even if you remove only one coin from the first pile in every move, after a moves, the first pile, which had a, will be empty. But the second pile will contain b minus 2a coins. And this is a positive number because we assumed a is less than b by 2, which means 2a is less than b, which means b minus 2a is greater than 0. We'll be left with some positive number of coins in one pile and no coins in the other pile, so no more moves. So this was arriving at the necessary conditions with a quick intuitive analysis. Now let's be 100% sure that our intuition is correct and there are no flaws in our thinking. So we'll go step by step rigorously. Let a and b be the number of coins in two piles where a is less than or equal to b. It is just labeling the two numbers. The smaller number, we'll call it a. Let both piles become empty after performing x moves where we remove one coin from the first pile, 2 coins from the second pile. And y moves where y is the other type of move where in each of this move we remove 2 coins from the first pile and 1 coin from the second pile. So we get these equations. Okay, let us take a look at it carefully. We had a on one pile, a number of coins, b number of coins in the other pile. So let us consider the pile that had a number of coins. How did we make that pile empty? We're calling that the first pile, the pile with a number of coins. We made it empty by removing one coin x number of times. So this is the part that we should be focusing on. And then removing 2 coins each in y number of moves. So a equals x plus 2y. Similarly, analyzing the second pile, we'll find b equals 2x plus y. And these two equations itself immediately gives us the first necessary condition. And I'm doing all of this mechanically, and I have a reason for doing all of this mechanically because I don't want to get biased by my intuition. I'll just follow the mathematics mechanically without any emotions, without any intuition, just to make sure that it works out correctly. So that is the intention behind just following the steps mechanically, and it should match what we found with intuition. So now we'll just add these two equations. A plus b equals 3 times x plus y, and this is showing that if we have been able to make both piles empty, a plus b is a multiple of 3. Okay, so this is just noted down in a different notation, but this is the first necessary condition that we have arrived at. Second necessary condition, where we have seen that a has to be greater than or equal to b by 2, or another way of saying is that b should not exceed the double of a, that is b is less than or equal to 2a. So solving the two equations, again, we solve the two equations, we find what is x and what is y. It turns out to be like this. So it's just plain straightforward solving system of equations, and we get this, and we can take a look at this first equation. So since x is greater than or equal to 0, so we know that there are non-negative number of coins in each pile. So since there are non-negative number of coins in each pile, x is greater than or equal to 0, which means 2b minus a is greater than or equal to 0, which means b is greater than or equal to a by 2. But this is not an interesting conclusion. We did not learn anything interesting here, because we have already assumed that a is less than or equal to b, and we are reducing a further. We are making it half, so obviously this will be less than or equal to b. So this is not interesting. Let us look at this one. Here we see y is greater than or equal to 0, and we get again 2a minus b greater than or equal to 0. That implies a is greater than or equal to b by 2, and this is the other necessary condition that we stumbled upon for intuition. So from this we know that if either of these conditions is violated, then we don't have a solution. That is very easy, because these are both necessary conditions. But does it guarantee that if both these conditions are satisfied, then we will have a solution for sure? Is that guaranteed? And no. So from the analysis that we have done so far, that is not guaranteed. So we have to go and prove the sufficiency of these conditions. We have to show that if both these conditions are satisfied, that is sufficient for a solution to exist. So that will come next. So I'll consume an extra 5 minutes to discuss that, and that is what I meant by the school abbreviation that I had in the scratch buffer. It is also called as TONCAS. So we are seeing an example of TONCAS right now. The TONCAS is the obvious necessary condition is also sufficient, and it happens in many mathematical problems, many algorithm problems. We often see that the necessary condition also turns out to be sufficient, but it does require work to show that the necessary condition is also sufficient. There are problems where this will not be true. There are problems where the necessary condition is not sufficient, but in many we do have this. So this is one such problem, where the necessary condition is also sufficient, but we need to do the work and show it. And in this case, it is just doing whatever analysis we have done here, doing it in reverse, and it shows us the sufficiency of these conditions as well. Let us do it in an extra 5 minutes that will take now. So let a and b be the number of coins in two piles where a is less than or equal to b. So this is the same assumption, same terminology that we did earlier, and this time we are assuming that these two conditions are satisfied. That is, a plus b is a multiple of 3, and a is greater than or equal to b by 2. That is, b does not exceed double of a. B does not exceed twice of a. We're assuming all this is true, and now if we can show that this guarantees that a solution would exist, then that establishes the sufficiency of these conditions. Let us take a look. We will now show that there exist non-negative integers x and y such that both coin piles become empty after performing same thing like before. X moves where we remove one coin from the first pile, 2 from the second. Y moves where we remove 2 coins from the first pile and 1 from the second. So that is, we will show that there exist, and these are the things we have to show. So I have underlined each one of them with different colors. These are the important things that we have to remember to prove, otherwise our proof will not be complete. So we will show that there exist non-negative integers x and y such that they satisfy the equations this, because we started with a number of coins, b number of coins. We explained x moves of one kind, y moves of another kind, and we saw in the previous board that that means satisfying these equations. Now we have to show, and if these equations hold good, then we also know what x and y is in terms of a and b. So x would look like this, y would look like this after solving the equation. But what is not guaranteed is, what we have not shown yet is that these are integers. If these are fractions, then that is no good. That means we don't have a solution. But if these are integers, that is one thing we want to show. So we have to show that both are non-negative integers, not just integers. If they're negative integers, again, it is no good, because our moves cannot be negative in number. Our moves will be non-negative in numbers. So we have to show that these are both non-negative, which is the orange underline here. Both have to be integers, that is the green underline here, and both satisfy the equations this, which we are sort of assuming for now, I guess. I have done it elaborately anyway, once more, so that is fine. let us see each part of it now. The non-negativity of x and y, and this is just doing the previous argument in reverse. That's all we are doing. So we know that a is less than or equal to b, which means, and I'm again going mechanically, throwing away all intuition, we get 2b is greater than or equal to a, which means this numerator is greater than or equal to 0, because 2b minus a will be greater than or equal to 0, which means x is greater than or equal to 0. So this is non-negative. We have not shown that this is an integer yet. Non-negative, okay, so we're making some progress there. Then since a is greater than or equal to b by 2, and this is one of the conditions, important conditions, we get 2a is greater than or equal to b, which means 2a minus b is greater than or equal to 0, which means this numerator is greater than or equal to 0, which means this is non-negative. Non-negative, real number. We have not yet shown it as an integer. Now we'll show the integer part. Again, it is all about doing the previous stuff in reverse. So we know that a plus b is a multiple of 3. And that is a given condition here. We are trying to show its sufficiency. So a plus b is a multiple of 3, and we'll use modular arithmetic here. So subtracting both sides by a. So here we get just b, here we get minus a. So minus a is congruent to b modulo 3. Now I'm going and adding 2b on both sides. So I get 2b minus a on left side, 3b on the right hand side, which means 2b minus a is a multiple of 3. That's what we're saying, because 2b minus a is 3 times something. So 2b minus a is a multiple of 3. This is a multiple of 3, which means x is an integer, because a multiple of 3 divided by 3 gives us an integer. Similar analysis for this part also. There also we do similar tricks, and we show that 2a minus b is a multiple of 3, which means this numerator here is a multiple of 3, which means y is an integer. So we have shown that starting with these assumptions, we will get some moves, x number of moves and y number of moves, such that both are non-negative integers, and they indeed satisfy this equation, because the way I got these expressions is by solving these equations. But in any case, for the completeness of the proof, what we will do, we'll take this x and y, plug it back into these equations, and we will see that x plus 2y will become a, and 2x plus y will become b. So it is also satisfying those equations. And that is how we have come to this conclusion that the conditions, those necessary conditions are of course required for a solution to achieve. And if those conditions are met, it is also guaranteed that a solution will definitely exist. And that is how we can go ahead and write a simple code now, relying on the necessity and the sufficiency of these conditions. And the code looks something as simple as this. So if a plus b mod 3, so basically this is saying if a plus b is a multiple of 3 and 2 times a is greater than or equal to b, then we have a solution. In the other case, we don't have a solution. So while we began the analysis, this part was easy to understand because this was a necessary condition. This required a little bit more work to show that when we have this condition, we also definitely have a solution. All right then, so that brings us to the end of today's session. It took 6 extra minutes. I'll just quickly check if there are any comments to be shared by anyone about what we have studied so far, or if you have any alternate interesting solutions to share about this. Okay, no comments. In that case, we are ready to end this session. This was the last session of this week. We'll meet again next week. I think it will be Tuesday. I will be updating the schedule on the channel, which is our IRC channel. And if you go to the homepage of offbit.cc, our computation club, if you're not in the channel already, please go through this page and you can join this channel. For those who are not used to IRC, you can join this matrix bridge. It will be much more convenient, and that is why I publish the schedule, and we also discuss the plan for the upcoming sessions, so we can talk there. So with that, we'll end today's session. Thank you all for joining the sessions almost on a daily basis. It keeps the sessions fun. We are going to meet again most likely on Tuesday, same time 1700 UTC. Until then, take care and goodbye.